So thank you so much for inviting me in this wonderful place. It's always great to be here. So actually, in a sense, it's a two-part talk. So the second part will be given by Takeshi. So the subjects are very close. And I recall that the notion of singular support, well, in algebraic geometry, it comes from the theory of d-modules, where this notion is somehow at the very basic for the development of the theory. And the notion of holonomic d-module is comes just from the very beginning of the story. Well, and you can ask if the corresponding theory comes in the étale story, in the story of étale constructible sheaves. After all, you have in over complex numbers, you have Riemann-Hilbert correspondence, which identifies holonomic d-modules with regular singularity with perverse constructible sheaves. And the corresponding theory, it was developed in the setting of real analytic varieties by Kashiwara and Schapira, but until now it was not developed in the étale setting, and I will try to explain how at least the first part of the theory, which has to do with the notion of singular support, the second part, which has to do with multiplicities of singular support, the characteristic cycle. I hope Takeshi will talk about this. And in a sense, it's pretty strange that all the story was not understood 30 years back, because as you will see now, well, all the methods were readily available back then. Well, so let me begin with the statement of the theorem. So I will play with algebraic varieties over a base field K, which I assume to be perfect, of characteristic P. And I fix a prime L, which is not equal to P. And for an algebraic variety X, I will denote by d of X the derived category of constructible complexes. With coefficients in Z modulo L power n, some n, or you can do just Z mod L or L-adic, whatever you prefer. It's well, now constructible always means bounded. Well, now suppose that my X is smooth. And I have a constructible sheaf on X. Well, sheaf for me is just an object of d of X. Well, definition. The singular support of F, and the notation is SS of F, is the smallest closed subset of the cotangent bundle that satisfies the next property. Whenever we have an open a pair of F and U is an open subset inside of X, and F is a function on U, such that if you consider the differential of this function and consider it as a section of the cotangent bundle on U, then it will not intersect, it will be disjoint from the singular support. Well, so given such a pair with that property, it should imply that all the vanishing cycles, well, the vanishing cycle sheaf of f with coefficients in f equal to 0. Well, it's all the same. Also, I can consider maps to curves, and there is no difference. Well, probably yes. Probably you're right. I'm sorry. Yes, if the field. Well, probably you're right. Well, if I have a non-rational point, well, I would think this is enough. I cannot. Certainly it would be enough to say that it will be the same over any finite extension of the base field. But I would think that this is enough. Well, this is a definition. Now I would state the theorem. The first part of it. No. Well, I consider function and consider the vanishing cycles. It is a sheaf on the zeros of the function. Pardon? It is a sheaf of vanishing cycles. Well, it is clear that such a thing is automatically conical. So you can conical means that it's if I consider the action of group of homotheties on T star x. Yes. So that's a nice thing. Yes, it's essentially obvious for such things. They form a filter naturally, and the reason for this, the main reason, is that if you have a function, with this property with respect to, that the vanishing cycles, they have local origin, and so if you have a function which satisfies, you have two conical subsets such that over intersection, it satisfies over intersections, and locally on the neighborhood of every point, it will be disjoint with either one conical set or another. But here it's important that it's actually a function with value in line or a curve. If you will have a function with values in a plane, that would be not automatical. U is a risky open. Yes, that's enough for the risky open. Okay, now the theorem. So I will formulate now the first part, that the singular support is equidimensional of dimension equal to the dimension of x. So it's a conical subset of the cotangent bundle of half dimension. A typical, so two opposite typical situations is one when we have locally constant sheaf, locally constant, say, non-zero sheaf, then the singular support is the zero section of the cotangent bundle. And if we have a skyscraper at a point, this will be the fiber of the cotangent bundle over that point. That's empty set. That's empty set. Well, pardon? Well, I assume that dimension is a function on X, or on the set of connected components of X. Ah.
So you can say that the dimension function dim sub x on SSF is equal to dim x?
Well, okay. Yes. Yes. Or that X is connected. Anyway, so fine. Well, now to formulate the second part of a theorem, I need some extra notion. And this comes as follows. So suppose that I have a closed conical subset inside of the cotangent bundle. And so I would like, so again, the second property will be that singular support actually satisfies much stronger property than the absence of vanishing cycles for functions. So, and in order to formulate it, I need to introduce some extra notion. So suppose that I have a closed conical subset, and I will, in the next definition, I will consider such correspondences. So they will look like as follows. So I have U, which maps to X, and this thing maps to Y. And this I will be denote mapped by H, and this will be F. And U and Y will be again smooth varieties. And I will call such thing, well, a pair of H and F, well, say test pair. And the next, so here is a definition. I will say that such a pair is C transversal if for every point, closed point U and U, it satisfies the following condition. So first, let us consider the map of the cotangent fibers. The differential of H at point U, so on the level of cotangent fibers. And what I want to know is that inside of the thing we have the fiber of the cone. And what I want to know that if I have a non-zero covector lying in this cone, then its image here will be also non-zero. Well, if this condition is satisfied, then I can consider the image of the cone by the map of DH will be a closed conical subset in the cotangent fiber. And if it's the thing satisfied for every point U in U, then this will form, all of them will form a closed conical subset inside of the cotangent bundle, and I will denote it by H upper star of C. So that's the notation. Now the second property, it again holds on U, and now I want to consider the differential of the map. Pardon? Yes, yes, I assume that both U and Y are smooth. And what I want to know that the non-zero cotangent vectors do not, their image will not lie in H0C. So certainly the first part of the condition, it holds tautologically if the map H is smooth. The second part, well, you see that if C includes the zero section, then, well, if C is, well, say it is a zero section, then this means that the map F is smooth itself. So this is the condition, and now I can, now another definition. Suppose that, so I have C, and suppose that I have a sheaf F on X, and I will say F is micro-supported on C, if for any test pair which is C transversal, the following thing holds. I can consider the pullback by H of my sheaf, and I want the condition is that it should be universally locally, that the map F should be universally locally acyclic relative to this sheaf. Now, a particular case is when U isn't just open, H is an open embedding. F is capital, yes. And here F is small. That the map F is universally locally acyclic relative to this sheaf. In case when H is an open embedding and F is a function, then this is just Y is just a line, then it is essentially this condition. Well, if I will compute vanishing cycles with respect to all translations of the function. Well, now the second part of the theorem stands that F is micro-supported So again, this condition is, well, it's clear that given any C which satisfies this property, it must contain the singular support. And the claim is that actually it is equivalent if a conical subset contains singular support if and only if F is micro-supported on it. Well, so for the rest of the time, I will try to explain the basic points of the proof. Well, I will use the tool, main tool that I will be using is geometric Radon transform that was studied by Jean-Luc Beilinson, and it goes as follows. So tools. So suppose that I have a projective space P of dimension n. Then I can consider the dual projective space PV. And so it's the space of hyperplane sections in P. And there is a standard correspondence, which I denote by Q between them. So a point here I will denote by X, here by X check, and here and the projections will be P and P check. Okay. Now, the Radon transform is the functor. You have this correspondence indices in the standard way, the functors between D of P and D of P check. Oh, sorry. And they're defined as, well, I will use shift just for convenience. And then it's clear that the two functors, if I will, well, that R is, well, it's left and right adjoint to R check twisted by n minus 1. So I permit myself to omit the twists. And one first important property of this transform that was observed by Beilinson is that though these functors are not equivalences of categories, their equivalence of categories pull back and push forward, and then I take shift by n minus 1.
So the star is a composition?
Yes. So I consider pull.
Between the P dual and the star?
Push forward. Well, I omit the derived functors, as is common. But it is their mutually inverse equivalence if viewed in the quotient of the derived categories modulus the constant complexes. In particular, well, or equivalently, the following thing holds that if I consider the adjunction map, say I have. They're both left and both adjoint from both sides. If I consider, say, here, and then I go back, and then I apply it to F, and then I consider the adjunction map, then the cone of the adjunction map is a locally constant sheaf, or which is equivalent, it's cohomology R. Constant. So that is the main property that I will be using in the next. Pardon? Locally means, well, if you have a complex, well, you could have global extension. So locally in the topology, everything. Well, if I consider a single sheaf, then locally constant means that it comes from the point. If you have a complex, then you would rather either say that it's cohomology or locally constant, or you permit yourself to localize. Yes, in all senses.
So you should have also a map in the other direction?
Yes, it is. Yes, also in another direction, but I will use it in one. In another direction, it will be another sheaf. Yes. Yes, I. I don't know. I should think. I don't know on the spot. Sorry. Well, I don't think so. But okay. Anyway, So I cannot answer the question. Now, apart from, so this is a part that has to do with correspondences, but I also need to consider this very correspondence microlocally. And the key thing is that you have canonical identifications. So if we have, and these identifications are called the Legendre transforms. Namely, let's consider the cotangent bundle to P. Let's consider Q, and let's consider the cotangent bundle to P check and its projectivization. Okay. And the claim is that those three spaces, they're identically the same. And this is essentially an obvious assertion. For example, how to define this identification. If you have, what does it mean that you have a point here? This means that I have a point in P, and I have a line in the cotangent plane to this point. A line in the cotangent plane, and so which is P, I mean, it's not Grothendieck notation, but rather dual, it's lines. Okay? So if I have a point in P and a line in the cotangent space, this is the same as a point in P and hyperplane in the tangent space. And the hyperplane in the tangent space passing to the point, it extends in a unique manner to a just plain hyperplane, global hyperplane passing through the point. And this is a point in Q. So it's essentially tautological, and this is a dual identifications. Well, now I can state an intermediate result, which is somehow, well, about one half of the theorem, and I will a result about the Radon transform, which implies it. Maybe let's call it theorem A. And it says that given any sheaf f on X, then it is micro-supported on some conical subset of dimension less or equal the dimension of X. So it's essentially the upper estimate for both assertions. Now, the theorem is deduced from a theorem about the Radon transform, and it is the following result. Suppose I have a sheaf G on P. Well, maybe before I formulate it, I need notation. Suppose I have a map of algebraic varieties, say Z to Y, and I have a sheaf F here, and then I can consider the largest open subset such that the map is universally locally acyclic relative to F, the map being restricted to this open subset is universally locally acyclic with respect to F. So the property of being universally locally acyclic is open property. So you have maximal open subset in Z with this property. And I will denote by E F coefficients in F its complement. So it's the smallest closed subset of Z such that F restricted to the complement is universally locally acyclic relative to F. Okay. Now with this notation, let us look. So suppose I have G. Now let's look at the diagram and let's consider the pullback of G. And I can ask, well, whether I can look at the second projection and I can ask whether my sheaf is universally locally acyclic, whether this projection universally locally acyclic relative to this sheaf. And the claim that the closed subset where it does not happen has dimension less or equal than n minus 1. So let me first explain why theorem B implies theorem A, and then I will explain how one, well, give an idea how one proves theorem B. First we reduce to the situation where my X is actually a projective space, and the reduction is very simple. You be, well, say X equals, say P check, F equals the Radon transform of some G. Well, basically, the main point is that if we consider all sheaves that satisfy theorem A, for which theorem A is true, then they form a thick subcategory in D of X. So in particular, and which contains or closed subsheaves, or all locally constant sheaves. And now the way to reduce to this situation is this. So maybe locally you can, our assertion, and again this subcategory, sorry, it has a local origin with respect to, well, the Risky or étale topology. So, this is a local question. So we can replace my X by a covering for which U, for which there is an étale map from U, say pi, from U to say, well, P check, and then given such an étale map, then you immediately see that F itself is a direct summand. Is a direct summand of push forward and pull back sheaf that just follows, well, you make base change and you immediately see that this is true, and since our these good sheaves, they form a thick subcategory, it's enough, it's enough to check that this type of sheaf is to prove the theorem for this sheaf. And again, because everything is local with respect to étale topology, we can consider this sheaf. And so we're reduced to the case where X is P check. And then we take for G the Radon transform of this sheaf. So we take and then we take Pilala star to F. And then again, since the cone of this map is locally constant and everything is known for this cone, therefore it's enough to prove the theorem for this sheaf, it's enough to prove it for that sheaf. And so we arrive to that situation. It is almost, but there is a little bit of an intermediate step. For you should also check that if the thing is micro-supported on C, then the direct image will be micro-supported on this extension of C, well as you do it in the cone. So you need to play a little bit. That's another possibility. But this is a little bit more immediate. So that is the first reduction. And now the second, so when we are already in the situation where then I can determine this closed conical subset C of which theorem A says. So in this situation, we just take for C the union of the zero section of the cotangent bundle and the affine cone over C. Now, what does it mean, the affine cone over C? C itself, so you take for C this set of which theorem B tells. Affine cone Okay, so this is a closed subset of Q, but also due to the Legendre identification, it is the same as projectivization of the cotangent space to P check. So given a closed subset here, I can consider the affine cone over it, and that is the thing here. Now, by theorem B, this thing has dimension less or equal than n. So this has dimension n, and this has dimension less or equal than n, because corresponding projectivization has dimension less or equal than n minus 1. And the only thing remains is to check that you actually have this property that the sheaf F is micro-supported on C. And this is pretty easy for the following reason. Maybe let me draw the diagram. So you have Q, you have the projection to P, the projection to P. Check. Now here you have this map, this standard thing we have for, we have a test pair. And then we can take the corresponding fiber product diagram, say QU, and let me denote it by H tilde, and this is PV, and this will be P tilde V. And now what we want to check is that, so we have here, we have my radon transform sheaf F sitting here, and then certainly it's if I consider the pullback by H of this sheaf, then since F equals here and here, then by the proper base change we will have that H upper star F equals well, and also we know that this map is proper. And therefore, if we want to check that F is universally locally acyclic relative to this sheaf, it's enough to check that the composition of these maps is universally locally acyclic with respect to pullback of G to QU. Okay. Now there are certainly two. There is so here we have this closed subset E, and well, since the map F is smooth because C contains the zero section of this cotangent bundle, we know that the map F is smooth, and therefore the composition is smooth, and therefore we know that outside of the preimage of this closed subset, everything is universally locally acyclic. So that's easy. Now the problem is to check on the subset, but if you just look at this diagram and look at the definition of C transversality, you see that on the subset, the C transversality implies that the map QU to the product of Y times P is smooth on the preimage of this closed subset in QU. And therefore, well, it's essentially that the universal local cyclicity property is essentially evident for we have smooth base change of a situation where we have constant family of sheaves. Well, now I have 10 minutes, and maybe instead of telling how you prove theorem B, which is variation, well, it's essentially it's proven by a variant of an argument from Beilin's theorem de finitude. 15 minutes, fine. Still, maybe I would like to say a little bit how to move outside of theorem B and what is needed for the rest of the proof, since it has to do again with geometry of the radon transform and the theory of Lefschetz pencils. And it also explains how you can see where the singular support, well, what is the singular support? Yes, it will. In order to explain the opposite thing, I need exactly this picture. So maybe recovering singular support of a sheaf from the ramification divisor. After a sufficiently high Veronese embedding. Well, on the radon transform side. Okay, so here is my situation. So I have my projective space P, and I want to embed it by Veronese into a large. So let's call it large. This will be the small projective space, and this will be Veronese embedding of degree d. And for the theorem, I need to assume that it's more than that d is more than 2. And here I have the picture of the radon transform on P tilde. Well, and I want to understand, so here I have a sheaf F, and I want to understand how its singular support looks like. So in order to do it, first I consider the push forward of my sheaf by the Veronese embedding, and then I apply the radon transform. So here's the radon transform, I again put tilde. Well, so for every sheaf, I can consider the maximal open subset of my projective space on which it is locally constant. And let us denote by D its complement. Well, now I can formulate the theorem. Well, maybe before I formulate, I need a small notation. So here the singular support leaves its a conical subset in the cotangent bundle to P. And there is a standard way, given a closed embedding of smooth varieties and a conical subset in the cotangent bundle here, there is a standard way to make it a conical subset in the cotangent bundle on a larger manifold. So it will leave over this closed submanifold consists of all cotangent vector whose restriction to P will live in C. So here's a notation. So if I have C inside of T star smaller thing, then the corresponding thing I will denote by E push forward of C in that sense, and it will live in this larger cotangent space. So after all these notations, I can formulate the theorem. So suppose that my Veronese embedding is of degree larger than 2, and then the following holds. So first, we know that D is a divisor. Well, let us denote by A its components. Pardon? Who is non-zero? F. Oh, the sheaf. Oh, yes, it is non-zero. Otherwise, it's empty divisor. I don't know if it's divisor or not. If you start with a constant sheaf, yes, then again it's an empty divisor. Oh yes, sorry. Yes, it is an actually embedding, so it cannot be. Yes. If it's a sheaf on a point, then this is just the corresponding hyperplane. So you view this point as a point in P tilde and consider its orthogonal hyperplane and the dual thing. Well, but it is a divisor. Now, the second assertion is that for every its component, there is a unique CA inside of the cotangent bundle to the small projective space we start with of dimension equal to n with the following property. Yes, conical. With the following property. So consider the corresponding conical subset inside of, well, extended as in a standard way here, and consider its projectivization. Well, then again, it is a conical closed subset of the projectivization of the cotangent bundle to the left space. Now I can again go by the Legendre transform here and project it to this dual projective space. And what I want, the property will be that the image of the thing will be equal to dA. So the third property is that if I consider this projection to dA, it is generically radical. And now the fourth property is that certainly is that the union of CA is exactly the singular support of F, and F is micro supported on it. Yes, yes.
Let us say, so if you allow projective spaces of dimension 0,
Uh,
and you cannot recognize the zero section of the cotangent because there are no divisors, so you must embed it in the projective space of dimension bigger than 0, otherwise you get
uh, well, certainly. Well, then divisor means something empty, yes, and
the constant sheaf is certainly has the zero section, must have certainly also the non-zero constant sheaf must have something in the singular support, which is the zero section of
stop. Well, okay, I'm ready to add the conditions that the dimension of P is more than 0. Well, so basically the story is like this: that if you just look at singular support, it's somehow pretty well, you cannot just see immediately how it looks like. But if you turn it, if you consider the Radon transform, then what happens is that the projectivizations of singular supports of a sheaf and its Radon transform are identified by the Legendre transform. And if we are in this situation, if we permit ourselves to make sufficiently high Veronese embedding, then after turning the picture to the Radon transform side, then there will be all the components of the singular support start to lie actually over hypersurfaces. These are components of the divisor. And so there are no components that are difficult to see that live over something of codimension more than 1. And moreover, you can recover this divisor itself is just simply ramification divisor of, well, in most situations, this ramification divisor of a local system. It can be that, that it's actually something that's exactly supported on the divisor, but it's a more rare situation. Well, so that is the story. Again, the proof about the estimate from the opposite side comes exactly for this reason, that that it is a ramification divisor. And the way maybe one other word to see this picture is like this. So the way you prove the theorem is that first, you consider now you look on the picture from the point of view of perverse sheaves, and then you first, it's pretty easy to reduce the theorem to the situation where our sheaf is actually an irreducible perverse sheaf. And then again, it's almost tautology that if you consider the minimal conical subset C on which your sheaf is micro-supported, not the, but A, actually, just a minimal, the smallest subset. So a priori, you don't know that it is uniquely defined, but it is, since it's singular support. And then you see that if you turn it by the Legendre transform, then its image will be exactly D. That is very easy to see. And in case when your sheaf is an irreducible perverse sheaf, this leaves you with exactly two possibilities. So maybe I should say that also you know that at least one of the components of D in this case is a hypersurface. for the reason that this hypersurface has to do with conormal to the support of your initial irreducible perverse sheaf. And then you know that by Beilinson, if you consider the Radon transforms, then it's all its perverse cohomology except a single one, they are locally constant, and in one of them there is a single irreducible Jordan-Gödel subquotient. And you immediately see that there are two possibilities, that either this irreducible perverse sheaf on the dual projective space is actually supported on this hypersurface, and this means that all other components disappear, or it is supported at the generic point, and then this D will be exactly the ramification divisor of the corresponding irreducible local system at the generic point. And you deduce the property of that it has the right dimension exactly from the property that the ramification divisor is of a local system is a divisor. Because you know that D itself, it contains a single, at least one component which is hypersurface. Because if you start with irreducible sheaf on P on the left side, take its support, then its C must contain the closure of the conormal bundle to this singular support. And that has right dimension, so if you transform it to the dual side, you will get hypersurface. So therefore you have... Yes, it is. Yes, and then since it's an irreducible perverse sheaf, it will be either supported on this hypersurface or supported everywhere. Then you have a single, then this D is exactly this hypersurface. There is no other components at all. For the reason that if you have, the thing is that Veronese embedding, it has the following, if this condition that D is more or equal to 3, it implies the following thing. Suppose that you have two conical subsets in the cotangent bundle of two such C's, which has dimension less or equal than n, like in our situation. Then, now you transform them and consider the image in P tilde. Then C will be contained in C prime if and only if the corresponding thing will happen there. So if you have two distinct irreducible components, then their images here, they will be also distinct. So it cannot be that one is contains another. And so if you have one hypersurface, then because of irreducibility, nothing can be outside of it. Well, probably that's it.